802.11 is the standard which governs wireless transmission of Ethernet. The major difference between wired and wireless is what is known as collision detection versus collision avoidance. It's an important principle to have in mind when you are doing designing for network access using wireless technologies. In the early days of Ethernet, there was problems with transmission over coaxial media where Ethernet frames were colliding, and there needed to be a way to do a retransmit of a frame should there be a collision, so the data could be transferred. And so there was listening on the wire for any type of collision with two frames traversing a media at the same time. And should there be a collision, it would be detected, and then the endpoints would do a retransmit following the Ethernet protocol. Nowadays, that's no longer applicable because Ethernet switches make collision domains isolated to every switch port. That's basically their function in life. The principle of collision detection still exists as a part of Ethernet. It's just not used anymore because everything is on Ethernet switches, and that eliminates larger collision domains. However, with wireless, it may not be known, even though there might be, 500 devices connected to a wireless access point or 7,000 devices connected to a mesh network. Each wireless access point can only listen to one device at a time. It's called collision avoidance. The way it does collision avoidance is there's listening on the media for anyone that is currently transmitting. If no one's transmitting, a frame is sent to the access point indicating that a device is ready to transmit, and then there is an exclusive communication session opened with that device in order to send and receive data. Once that is completed, the access point is then again available for other devices. So it's a one at a time approach to transmitting of data. And the question is, how can we use that hindrance? How can that hindrance be minimized? So what you're looking at is the 802.11 standard for collision avoidance. And it just looks as the channel idle, yes or no, and then there's a random back off. If it is idle, go ahead and transmit, and then there's confirmation, and so on and so forth. From a network perspective, that's the major difference between wireless and wired devices. Wired devices are connected to Ethernet switches, so there's really not the same limitation. Many things can be talking at the same time, and no problem. It all has to do with the hardware of the Ethernet switch, whether it's able to transmit and receive everything that is occurring on its circuitry at any given time. Great efficiencies. And so in many respects, wireless is a step backwards in our technology. But just because of the ease of use, it is very heavily adopted. Okay, so the wireless industry has matured greatly. And these two organizations, the CWNP and Ekahau, have stood out as the leaders for the formal training in wireless network engineering. Ekahau develops software and hardware also to some extent in order to perform wireless design um, documents. They're known as wireless predictives. So if you have a building, you can input the type of building material that is present in the building, whether it be glass, steel, drywall, drop ceiling, brick, poured concrete, God forbid, whatever is the type of building material, the thickness, the ceiling height, all those things into a Ekahau design document. And then you could choose what model of AP you're going to be installing and drag them out onto the floor plan, and Ekahau will automatically predict the coverage of a given area. And that way a wireless network designer can recommend locations or access points to be mounted. Typically, the recommendation is on the outside or the underside of a drop ceiling, if one is present. Not a 90-degree wall, but actually facing down is the standard approach for enterprise indoor wireless access points. Some people don't like, for aesthetic reasons, the view of access points dangling from drop ceilings, and they choose to put them above. There's a little bit of attenuation that goes through a drop ceiling tile, not that much. The overwhelming recommendation, though, is to mount them below on the outside of the drop ceiling. So there's no attenuation at all. One of the major problems with wireless is the attenuation issue, is how the signal degrades over distance. So it is a wireless network engineer's job in order to ensure that depending on the density of devices, that there be sufficient coverage for the network to be able to operate. And both of these organizations do a good job of training on that concept. Ekahau, again, is the leader in design software for wireless networking, and the CWNP is a professional organization that offers certifications on many different levels. These are the standards that Wi-Fi has gone through. As you can see, 97 is really when it first came out. And we're now looking at Wi-Fi 6 in the not too distant future. Ongoing debate about 5G killing Wi-Fi. I personally don't see that to be the case. And if you talk to the people who are getting ready to offer 5G, really they don't seem to think that it's going to be replacing Wi-Fi. Wi-Fi has its place within a office space as the most efficient means to provide data connectivity. If everyone is lit with 5G SIMs, the cost is astronomical, and you can provide faster or similar throughput using Wi-Fi for a much less cost. There's economies of scale that occur with Wi-Fi. If you're going to be taking certification tests, these are obviously going to be tested on. This is an important concept to also understand. The decibel level talks about how much the signal is degraded over distance or attenuation. When you're close to an access point, obviously you have very good transmission. When you're further away or you have objects obstructing you, you have less good transmission and low packet. You have higher packet loss. And when you're in the process of looking at how a network is going to be designed, you also have to take into account what the wireless network is going to be used for. If it's just going to be used for general mobility devices, connecting in order to do social media, then it's just very minimal what you have to do as far as the density of the coverage. If you're going to be running voice over IP phones with wireless chipsets, then the density of the access points needs to be greater in order to ensure that the decibel levels are good enough in order to allow for a packet loss free transmission of the audio of a voice over IP call or video call. And all those have to be taken into account when you're doing the wireless predictive.